Thank you very much. Let me just get a hang of this. Okay. Yeah. Well, hello, everybody. It's really an honor, and I'm very happy to be here at OHS. I had always heard about OHS, wanted to come, was never ever able to, so this is my first time here. Not my first time in Edinburgh. There's a nice story to that I'm going to tell you in a moment. But yeah, my name is Dan Alvarez. I'm an electronics engineer, and I worked on this satellite back then in 2016, 2017, back then. And it was at Universidad del Valle de Guatemala, which is the university in Guatemala that worked on this. So yeah, what is Quetzal? It's a bird. It's actually Guatemala's national bird. It's not endemic just to Guatemala, but to the region of Central America. You can see Guatemala up there in the center of the map, near Mexico, Honduras, El Salvador. It's a small country. And Quetzal is this beautiful green bird that has a long tail. And in Spanish, they call it la serpiente emplumada, which is sort of like the feathered snake. When it flies, the tail, since it's so long, it kind of shakes and wiggles like a snake. So it's a very majestic thing to see yourself. They're actually easier to see in Costa Rica, not in Guatemala, but they're quite beautiful birds. So what about Quetzal-1? That was Guatemala's first satellite. You see the finished, assembled, integrated satellite with everyone's tears inside of it right there. It's a CubeSat. If you haven't heard about that, it's standard for satellites that are cubes. They come in different sizes. This is the smallest one, which is 10 by 10 by 10 centimeters. And it was actually, construction began in 2014, and we deployed from the International Space Station in 2020. So that's 6 years there, and a couple of years before that as well, working on other ideas. And it operated from April, which was when it was deployed from the space station, to sort of November in 2020. So about 200 days. And it was an awesome 200 days for us once it started working. So just 2 slides on the history of the satellite. I mentioned we started a little bit before 2014, actually in 2012. We participated twice in the CubeSat competitions. You might have heard of those as well, which are sort of satellite in a can is sort of the idea. They don't get launched to space, but they get launched on a model rocket, and they go on a sort of, parabolic trajectory, and they have lots of sensors. They usually have an egg inside of them because they have to land and not break the egg, and that's sort of one of the tests that they do. So 2012, then after 2013, the second year that the university participated in the CubeSat competition, they started to think about what else they could do. The CubeSat idea surfaced. Passing from a CubeSat to a CubeSat is a huge step. And that's why it ended up taking 6-7 years to do it. But in 2014 was the first official team of 4 people that worked on the satellite. Back then we only had ideas and some CAD renders. There's, I think, one of the very first ones in the middle there. We didn't have much money, as many other projects here have experienced, and so we had mostly ideas and designs, but nothing physical yet. 2015, they built sort of a very first crude prototype. We wanted to manufacture our own structure from the beginning. There was a lab for CNC manufacturing. That was the first time we noticed that we needed better machining, better machines to actually do it, because this first structure ended up weighing about 1/3 of the CubeSat's maximum weight, and that was way too much. But that was a first idea, and quite impressive for the team that was doing it at the moment. Then we also had some crazy ideas. At some point, we thought about deployable solar panels, which was way too much for a first satellite, but we thought, you don't even really know what a power budget is at that point, and you just think you need lots of power, so you deploy their solar panels and just make it more complex than it needs to be. But we got good at the renders, at the CAD modeling as well with that. Then I skipped 3 years to 2018, but something very special happened in 2017, 1 year before the render you see in the middle, which is we won the Kibo Cube competition. That's a Japanese Aerospace Exploration Agency competition together with UN. And we won that on the second round of that competition, and that secured us our launch, which was huge. The launch is probably the most expensive part of it, or one of the most expensive parts of of getting something into space. And so we had that secured, and now we had to actually build the satellite. We had designs, renders, we had teams working on so many of the subsystems, but we didn't have an actual satellite yet. That render is actually quite close to what ended up being the satellite, and what ended up being the satellite is on the last picture. That picture is quite special to me, and it could be to you as well right now, because it was taken about half a mile from here. We actually did testing on satellite at the laboratories at the Royal Observatory. That's about half a mile from here. So we were here 6 years ago doing that. And I passed through the University of Edinburgh and took a picture outside, and didn't really know I was going to come back to do this. So that's quite nostalgic. So yeah, that picture was taken once the satellite was certified to fly. We did vibrations testing here, so on the shaker, and also thermal vacuum testing. So yeah, then it was deployed. 2020 was that. We were already in the pandemic, so we only saw the live stream, and no one got to be at the university except a couple people to see the live stream at the university. Many others got it outside, but that was the moment it came out of the launcher in the Kibo module on the International Space Station, and that was almost the last time we got to see it. We also got to see it very far away from the space station there, and there's a little snippet of the zoom of the satellite. And at that moment, the astronaut that launched it, which was Chris Cassidy, was talking to us sort of over the radio from the ISS when they launched it. It was very special. So yeah, that's the story. That's what we did. It took a long time. It took lots of people. I am here in representation of hundreds, so I'm very honored to be that as well. So I want to talk about the hardware. This is what excites me the most in these talks. Maybe we didn't get too much to talk about the hardware, and this is the Open Hardware Summit, so finally I get the chance. So about 70% of the satellite's hardware was developed at the university. This was not necessarily a conscious decision, but a monetary decision. It's very expensive to buy sort of space-ready hardware, and they sort of close that system up. So if you buy something, you have to buy other things around it, and it becomes, sort of a rolling snowball. But yeah, we built about 70% of the hardware. This picture is very special because it's the first time we sort of not disassembled. We put together all the parts the satellite needed. So that's the whole satellite, but we need to build it after that. You see the green PCBs are some of the subsystems. The black ones are the solar panels on the outside. Then you also see part of the structure. They're on the third row from the top, and a whole bunch of harnessing and other things. So I'm going to go through some of the subsystems that we built. The attitude control and determination system was one of them. First one, because that's the one I worked on during my time at the university. It was a passive control system that used sort of a magnet essentially, and it would align the satellite to the Earth's magnetic field, and that would sort of control the orientation. And also determination, which is where is the satellite pointing, We also worked on the antenna deployment mechanism. This one was quite ingenious and nice. We bought the antennas, but we did not buy the antenna deployment mechanism. That was another $4,000 or something. So we built the mechanism. It was very simple and not, at least simple to explain, hard to verify that it would work when it was launched. But it's a nylon wire running through a resistor. The resistor would heat up, and then the nylon wire would burn. The antennas were spring-loaded. They would come out. They would they also were pressing a switch so that we knew that they actually came off. And so that was the deployment, because these satellites get launched sort of in these sort of launchers that are like a rectangle. They come out, so they have the antennas closed in, and they have to come out once they've been deployed. So that's a really cool system. The electrical power system, that was probably the most complex board on the satellite. It would take in the energy from the solar panels, charge the battery, give the voltages and all the things that the subsystems required. Yeah, one of the most complex ones, and I think one of the ones we're most proud of having actually done. The payload satellite had a camera on it, but it didn't only have a camera, but we were actually trying to do sort of what's this called? Well, take pictures at different wavelengths to be able to analyze these pictures of bodies of water at different wavelengths to detect. In this case, specifically, was chlorophyll in Guatemalan lake. And you usually do this with multispectral cameras, but we wanted to do it with a monochromatic camera and just put different light filters in front of it. So we had a motor that would turn sort of a carousel of filters and put one in front of the other on the camera and take pictures like that. So that's what you see up the top of the image or at the bottom of the diagram. That's the filter carousel. We also worked on the ground control station, which was also very special to me. I worked mostly on operations for the satellite when it was in orbit, so I was constantly using this ground station for that. And then some things that aren't necessarily related to the satellite, but lots of testing that has to be done. We designed this test fixture for the vibrations test. This is actually a picture here in, where I said we did the tests about half a mile from here. And also this was a thermal vacuum test. We took this picture right before we closed the door to the thermal vacuum chamber. And the satellites on the left there, and a couple of us that came to Edinburgh to the test are there on the right. I want to talk quickly about the software. All of the software was written as well by us. And we had an onboard computer, which was not designed by us, but bought. And it was in charge of, data collection, transmitting telemetry, just monitoring and controlling all the other subsystems. And then we had microcontrollers in each subsystem, which were running on top of Arduino. All of that code on the subsystems was written by undergraduate students. I really haven't mentioned it, but most of the satellite was built by undergraduate students. We don't have a master's or doctorate in Guatemala, and not in this specifically, not in aerospace. But it was quite a challenge, but very rewarding. So to come, to OHS, I wanted to talk about, how the open source community, software and hardware, really helped us get here. We would not have been able to be here without the support and just the willingness of people to show us how things are done. So, hardware was based on openly available designs from either just people that would put things up or, some of the famous companies that we all love about open source designs available. Also, all the software running on the subsystems was running on Arduino and many open source libraries as well. And the ground control station was also running an open source software called New Radio, if you've heard of it. Very cool thing. And that's what we wrote all the sort of decoding and encoding software for the satellite. And so how do we want to give back? Because we always had that in mind, we know how hard it was for us to get information on how to build a satellite. It was very hard, and many things weren't available. So we wanted to give back in the best way we could. So we ended up releasing about 2 years ago the design files for some of the subsystems, 3 specifically: the electrical power system, the attitude control, and also the antenna deployment mechanism I mentioned. Also, the flight software for a couple of these subsystems is available. The software running on the ground control station was available. Actually, that was available from launch because we released it so that all of the amateur radio community could use the software to decode our data and send it to us as well. That was invaluable for us to collect data for the satellite. Our ground station would get data, but that was maybe like 5% of the data we got. The other 95% came from all over the world. The satellite would go over Guatemala at the orbit of the ISS about twice a day. So we would only get 2 passes, and of those, maybe 1 was good, because the other one was too far away. So yeah, that was open sourcing data collection. That was great. And the telemetry, we got all this data. We didn't get it. The people got it. So we also released it. And then the pictures that the satellite took, those are also available. We also wrote a couple papers on this. We're actually very proud of the work on that. It took a long while, as anyone that has done this knows. But we wrote papers on essentially how did we design these subsystems and how did we test them, how they performed, and how not to do it as well. this, I think, is one of the things we want to do, this is what we wished existed when we were doing it, and maybe it did, but it was hard to find. So this is sort of the idea. So just to end my talk, why build a satellite in Guatemala? I like this slide. It's just kind of, nostalgic and sort of melodramatic. But yeah, the first satellite, 1957, we all know. And then Guatemala came in about 60 years later with the first one. This picture is also from here in Edinburgh. Yeah, we're still very proud of it. But actually, what the main mission is for us, really, what ended up being so important for us was just to teach people in general, children, that these things can be done in countries that otherwise you would think maybe they can't do it, and once we start doing these things, we notice that, hey, maybe we're not so behind, maybe, of course, we have other limitations, but I think not related to being able to gather knowledge. Everyone's able to do that. You just need sort of the opportunity that pushes you forward. So we wanted to teach children that it could be done. This is a picture of one of the many sort of workshops we did. We 3D printed the satellite, and we would have children build it. We gave them sort of like the design, essentially, the how to put it together. And Quetzal-1 actually sparked the very first aerospace lab in Guatemala. This is a picture of that taken early this year. We're working on another satellite. Hopefully, Quetzal-2 will be launched at some point in the coming years. And many undergraduate students, again, it's not me doing it. It's not the team that was there. It's new people coming in that they heard about the satellite. They wanted to get involved somehow, in aerospace. And we're now sort of helping them, coaching them. Many of us got some experience from the first one. We also have a lot to learn, but I think that sort of fosters that knowledge. So that is it. I said that there's things released on GitHub. Oh my God, I have an alarm. Sorry. I said there was things released on GitHub, so you can scan that, go to our profile, or contact us. That email is in Spanish, so it's satellite with one L, not two. Or talk to me if you see me around. Thank you so much, everyone.